first thing that happens is we don't want to have complex numbers, but mathematics says you must. It's a fundamental theorem of algebra. To solve these problems which have eigenvalues in them, you have to solve polynomial equations. They have roots in complex plane. There's nothing to do about it. Okay. So we say, it's not because of quantum mechanics. We just have to use complex numbers. Second thing is, in almost all physical problems, we tend to implement them as a finite computation. It could be computation of methane for chemists or something with zillion basis functions, but finite number. So we're always looking at matrices acting on vectors. And there are two kinds. One kind is essentially a coordinate transformation in physics. But it just says, I can look at this thing this way or that way, and it looks the same because it has a symmetry. That's implemented in one complex dimension by having a phase, and in many complex dimensions by having unitary matrix. And it has to be unitary because we want to make sure that it doesn't stretch things out. When you rotate, you don't want to rescale lengths. And that's why this shows up as it times its complex conjugate has to be unitary. So it just rotates but doesn't distort. Second thing is, we bang our system with something, and that's called a measurement, and it says it's 3 inches tall or 17, pounds heavy, or it's twice as big as the other thing, whatever. So I get a number, and that generalizes to Hermitian matrices. So Hermitian matrices are glorified real number. Then there's this amazing theorem, we proved it. Then fact number 2 is known as Schur's lemma. And it says the same thing that we know from our discussions of projection operators. What we found with projection operator is that if you have one of these Hermitian matrices, the measurement matrix that bangs at some, what it does is you apply it to your space and returns some numbers it measures. But it turns out every matrix has its own natural coordinates, and they're given by the eigenvalues and eigenvectors of that matrix. And in those natural coordinates, the answer is one of the eigenvalues because it acts along one direction in the eigenspace. And that's what projection operators did. And this works like charm on any physical system we're interested in, as long as that matrix commutes, what does that mean? It just means that it doesn't matter whether I first do a measurement, then I apply my operation, my group symmetry, or I do the symmetry first, and then I apply the measurement. And that just says that symmetric object, if I measure in any direction measured by symmetry, has the same height or something. So that's a crucial thing. But this is here used as a gateway to a very fundamental thing about finite groups. And that's a focus of a few weeks, 3 weeks maybe of this course, is that finite groups have finite number of irreducible representations. These are representations that cannot be made smaller. These are smaller matrices that you can use to build up the big space matrices, but you can't make them any smaller. That means irreducible, cannot be reduced. And technical statement is that if my operator commutes with my projection matrices, it has to be proportional to 1. if it's not, when we diagonalize it, having the same enter in all diagonal places, then it will actually start splitting up and mixing up the spaces we have previously separated using our projection operators. So irreducible representation is one that cannot be split into smaller pieces. And, we worked on it. It's straightforward algebra. We did it, and we are done. This shows lemma.